Welcome back to ChemExam Explained, where the aim is chemistry clarity exam mastery. In this video, we will be looking at Cape Chemistry Paper 2, Unit 2, Module 1, 2025. Let's go. Number 1. Figure 1 shows compound A and compound B with two possible isomers of C7H16. So here we have our compound A and compound B. Part A, 1. Name each of the following compounds in figure 1. So if you look at this, the first thing we want to do is to identify the parent and then the branches. So here we have a branch on the second carbon, another branch on the second carbon, and the third branch on the third carbon. We started numbering from this side because we have more branches on this side than this side. So we have 2, 2, 3 trimethyl butane. For compound B, here we have a straight chain and of course 7 carbons, and it is an alkane because it's all single bonds, and it is heptane. Part 2. Define the term structural isomerism. Structural isomerism is the existence of compounds with the same molecular formula but different structural formulae. As you can see, these are the same in terms of C7H16, but the structures are different. This is a branch chain, and this is a straight chain alkane. State the type of structural isomerism present in compound A. Well, as you can see, all we shift around was the carbon atoms. Therefore, it is chain isomerism. A part 4. Describe two types of structural isomerism other than the one given in A part 3. Draw examples of displayed structures of each type. So in type 1, we have functional group isomer. And this is where compounds have the same molecular formula but different functional groups. And as examples, we could use aldehydes and ketones. These are two functional groups. We could also use alcohols and ethers, or esters and carboxylic acid. We could also use an alkene and cycloalkane. Those are all examples that could be used to show functional group isomerism. Type 2, positional isomers. In positional isomerism, what we're looking for are compounds with the same molecular formula but different position of the functional group. And the example we're using here is propan-1-ol, where the OH group, the hydroxy group, is on the first carbon. But now we have the hydroxy group on the second carbon here. So we have propan-1-ol and propan-2-ol as our examples of positional isomers. Part B. Another hydrocarbon having the molecular formula C5H10 undergoes oxidation reaction with acidified potassium permanganate to form two products, R and S. The products were subjected to analysis seen in the table. So we have PCl3. Now, what I'm seeing here is they say dense white fume observed. So I think this is a mistake because the dense white fume should be observed with PCl5 and not PCl3. Or it can be observed with SOCl2. But these are acylating agents that will identify the presence of a carboxylic acid. And in this case, we realize that if we get a positive result with our acylating agent, then our inference, our conclusion is that we're looking at a carboxylic acid. Because what the acylating agent is doing is it is converting a carboxylic acid into an ethanoyl chloride or an acid chloride. So in this case, this is the acid, and the acylating agent is going to cause this OH to be replaced with Cl. All right? And so we form an acyl halide. So the first part is identifying the carboxylic acid present. In part two, we are confirming that an acid is present because blue litmus paper was placed in the product R and we realized that the blue litmus paper turned red. Now, if red litmus paper was placed there, then it would remain the same. So it is suggesting again that our group is an acid group. Our other product S was divided into two portions and we use 2,4-DMPH that was added to product S. And as we know that an orange precipitate is giving confirmation that our product S is either an aldehyde or a ketone because Brady's reagent, which is our 2,4-DMPH, is identifying the carbonyl group C double bond O. And once that group is present, we will get a orange precipitate. Then for part 4, to the second portion of S, a small amount of Benedict solution was added and no observable change was seen or a blue color remains. So Benedict solution is blue and once you add it to your aldehyde or ketone, we don't know which one is present, so we're trying to establish that it is an aldehyde or a ketone. Now, if an aldehyde was present, then we would have the aldehyde changing the color of the Benedict solution from blue to brick red. And because an aldehyde was not present, you have no observable change. So we are confirming that instead of an aldehyde forming, what we have for S is a ketone. And so the Benedict solution, which is a weak oxidizing agent, is suggesting that our ketone cannot be oxidized. And so we get no further change. So for part 1, we are just to complete the table, which we just did. And then for part 2, based on the observations and the inferences in part 1 to 4, we are to predict the functional groups of product R and product S. And so we know that our functional group for R is carboxylic acid, and our functional group for our product S is a ketone. So let me explain this a little further as to why we have this observation and the conclusion that we have a carboxylic acid present and a ketone. Our hydrocarbon is C5H10, so we are confirming that it is an alkene. So CnH2n is the formula that we're using to confirm. So C5H2 times 5 is equal to C5H10. However, in order to get a carboxylic acid and a ketone, we cannot use a straight chain alkene. So that's 1, 2, 3, 4, 5, 9, 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we cannot use a straight chain alkene. What we'd have gotten here would be only aldehydes, which are then oxidized to carboxylic acid, but we wouldn't have gotten any ketone. So what this is suggesting to me is that our alkene is a branched alkene. So let's go with C, C, double bond, C, C. So that's 4. And now we have a C here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And now, if we oxidize this alkene, we'd break it here, forming an aldehyde, because oxygen will be added to both sides. So the aldehyde will be added here, and oxygen will be added here, forming a ketone. So what we'd have pretty much is C, C, so this carbon, and then this carbon with our double bond O, that is our ketone, and we're going to just draw it out in a straight chain. So that's C, double bond O, C. So this is our ketone, and these are H's around it, around the carbons. But this side now, what we have for this side now is our C double bond O with a H and then CHHH. And so we're going to write it the way that you can see that it's an aldehyde. So let's write CH3, separate that, C double bond O and H. So here we have a ketone and an aldehyde, but our hot oxidizing agent will cause our aldehyde to further oxidize to carboxylic acid. And so our final product will be R and S. So B part 3. Draw the displayed structure of either product R or product S, which is formed from the oxidation of the hydrocarbon. So you can draw for R, our carboxylic acid, ethanoic acid, or you can draw S, which is our ketone propanone. Part 4. Name and draw the displayed structure of the hydrocarbon C5H10 that was oxidized. So based on what I showed you earlier, it had to be a branch alkene and not a straight chain alkene. So our alkene that was oxidized was 2-methyl but 2-ene. So you form your ketone and your aldehyde, which is further oxidized to your carboxylic acid. Part C. Figure 2 shows a diagram of a polymer. Polymers play a crucial role by providing basic structural materials and participating in vital life processes in organisms. So here we see our structure, and these are our repeating units. You can see them right here, repeating units. All right, so what you do, you want to first look at part 1, which is to deduce the monomer used to form the polymer in figure 2. So here we have our styrene or our phenyl ethene as our monomer. So what you do is you look for your repeating unit and simply add a double bond, and that is your monomer. E part 2. Using the diagram in figure 2 and your response from C part 1, explain how addition polymers are formed. So the double bond in the monomer opens up at the sides and the monomers join to form the long chain polymer of 50 units or more. Part 3. Identify the reagents used and describe the color change expected in order to distinguish between the polymer from the monomer. Now we know that our monomer would consist of a double bond, but our polymer consists of single bonds. So we're going to use the test for unsaturation. Now aqueous bromine can be used, which is going to change our color from orange brown or red brown or simply brown to colorless. In other words, the monomer would decolorize the bromine, but the polymer would cause no change. And this is called the test for unsaturation. You can also use bromine liquid, which is bromine in CCl4, an organic solvent. And the same observation would be observed where the bromine would be decolorized by the monomer, but not the polymer. Part 4. State 2 characteristics of condensation polymers. 1. Condensation polymers are formed by the elimination of small molecules, example water or HCl. And 2, they form functional groups, linkages such as ester or amide bonds. So your ester bond would be your C double bond O in between carbon groups. And your amide bond would be C double bond O connected to a NH bond. And this would be your amide link. Part 5. Condensation polymers may be classified based on the type of linkages present. List 3 examples of condensation polymers. So our specific example would be a polyester, namely terylene, your polyamide, namely nylon 6,6, or protein, your polypeptide. This ends our question 1 for our Unit 2, Module 1, 2025. Thank you for joining.